So the last thing I'm going to do is look at some minor applications for matrix algebra and finance that we use. So the first application is bootstrapping bond prices. So let's see, we have a bond that matures in a year, and at maturity it's going to pay $105, and the price is $98.70. We have a 2-year bond that pays coupons of $7 and $7 at maturity plus 100, and its price is 101. And we have the price of a 3-year bond that pays 3, and 103 over the next 5 years. So what we want to do is find some internally consistent prices of bonds. So let's say we have the price is 98. I don't know. Let's just say we have P equals the cash flows of 105.00, 107 and 0, and 33103. And we want to find some discount factors. Where these are the present value of $1 a year from now, a dollar received 2 years from now, a dollar received 3 years from now. And so we can get these discount prices and maybe value some other bond that has, let's say, pays $20, $20, and $120 over the next year. So what is the the price that is consistent with these values over here of a 20% coupon bond? Well, one thing we can do, let's go to Excel. We have P equals CF times discount factor. So let's go back, I'm sorry. So we have P equals the cash flow times the vector of discount factors. So we take the inverse, pre-multiply by C inverse on both sides. And so we get D is equal to the inverse of the cash flows times the price. So let's see what that is. So highlight all this stuff over here. Matrix multiply, the inverse of cash flow matrix, and the prices. Okay, so, whoa, this is kind of funky. So a weird term structure, but this is how the prices that were internally consistent. So if we have a bond that pays $20, $20, and $120, what should be the price of that bond? Well, it should be the multiplication of these cash flows times the present values of those dollars. So the first 20 is going to be multiplied by, it's only worth 94 cents per dollar. The second is 89 cents per dollar. And, okay, let's just see what we got here. So it should be worth $135. And if it's something different, that's kind of an arbitrage opportunity. Let's see what I got here. Oh. All right, so here is the term structure. We have the 1 year rate is around 3%, 6%, 6.84. Well, that's one application. All right, the second application we're doing in 501 already is portfolio statistics. All right, so we have a portfolio weight that sums up to 1, and we have expected returns of stocks, bonds, and treasury bills. So if we want to expected return, it's going to be the transpose of the weights times W prime. So what do we have? So look at this. This formula right here is the weight transpose times the R bar, and it's this times that. So it's 6.45% return. And the covariance matrix is the transpose of W times the covariance matrix times the W. So this is W, And the standard deviation is just the square root of that. So we use it a lot in 504. And last, we look at calculating some coefficients for regressions. So let's say we have returns for Microsoft, or excess returns, returns minus the risk-free rate. And we want to measure this as a function of A plus B times the return on the market plus E. All right, so what we have right here is a return over 1 month all the way through 120 months. And that's going to be a function of A. Let's see. A times a bunch of ones, one for the first month, one for the second month, all the way down to one for the third month, times a market beta times the market return in the first month, the market return in the second month, down through the market return in the 120th month. All right, then we have some errors. Some error 1, error 2, all the way down through error 120. All right, so what we have is some scalars multiplied by a column, a vector of ones, and a column vector of market returns, and these errors. So what we want to do is solve for the A and B such that we're extracting all possible information about the market excess returns and Microsoft. So we got this 120 dots here, and we want to find the line of best fit, which has a slope, the beta, and some sort of intercept, the alpha. So we want to estimate alpha and beta. And so basically, you can call this vector y is our excess returns, and then we say that we can have our data is a vector of ones and a vector of market returns over the 120 months. So this is a 120 month, 120 by 1 vector of Microsoft returns. And then we have a 120 by 2 matrix of a coefficients of 1 and the coefficients of our values of 1 and the Microsoft return. And then we have our A and B. So 1 times A, B times that. So we get this value, and plus E, 120 by 1. Right, so one thing we could write this as is x equals, or y equals x is 120 by 2 vector matrix times A, B, right, plus E. So what we want is to solve for A and B such that we're extracting all the information. So what we'd like to see is that the epsilon transpose times x is going to equal, what would that be? 1 by 120. This is going to be 120 by 2. It'd be 0 and 0. So we want that error term to be orthogonal to our explanatory variables. So we don't want the error term to explain anything that our explanatory variables can. So we optimize our portfolio, optimize our estimates of A and B such that we get the most out of our x's. All right, so we can write this as vector y equals x beta, or this b is, let's call it beta, capital B. What's this E? So this is the A and B. And so if we take expectations, we say that y should equal xb, and let's solve for this b. Well, this is, what, 120 by 2, so we can't take the inverse of that, but what we can do is pre-multiply by X transpose X on both sides. And now this is going to be a 2 by 2 matrix. And what is this going to be? So it'll be 2 by 120. So this ends up being a 2 by 1 matrix. And what do we have here? This is a 2 by 1 matrix. All right, so now this thing can be inverted. So we can solve for beta as X transpose X inverse X transpose Y. All right, so we're going to use, hopefully you've seen this in MSF 502. So let's see how that works in Excel. So we have market returns, or Microsoft returns, market returns, and I'm going to say Y is the Microsoft returns, and X is going to be a column vector of ones and market returns. All right, so here I have my X transpose, so the W through X is my X transpose, and times the Y. So I get this 2 by 1 vector here. And so the X transpose X, I got the transpose of X times X, and this is 2 by 2. And so I'm going to say the alpha and beta is going to be the inverse of X transpose X, which is ZA through A99 times X transpose Y. And so what I get are my coefficients of 0.01, the alpha of 0.01, and a beta, market beta of 1.43. And so if we look at how this stacks up with data analysis, we run a regression of up here is the market returns against the Microsoft returns. We have a constant in there, boom, bam, and yay, we get the same results. So we use this stuff a lot. It's just not something I'm throwing at you. So that's it, and I'll have another set of series on calculus.